Welcome to SanfordFlipMath. Sorry about the delay there. This is AP Calculus, and we are in Chapter 4 now, which is taken from the Calculus book by Finney, Demana, Kennedy, 3rd edition. And we are actually going to start using derivative stuff. So just a quick heads up that everything that we did in Chapter 3 is still necessary. Chapter 3 was all about derivative rules, how to take derivatives, and all of that stuff is deeply in play. What we're going to take a look at is in section 4.1 is specifically about something called the extreme value theorem, and which is about extreme values. Isn't that clever? Maximums and minimums, and then how we can find them and how can we use calculus to do that. Okay, so maximums and minimums, just a quick reminder that there are really a couple of kinds of maximums and minimums that we've looked at since Algebra 2 and pre-calculus. This is a maximum. Quick reminder that the maximum is a y value. Its location is an x value. And this particular maximum would be a local maximum, or sometimes it's referred to as a relative maximum. And that is because that it is not the biggest maximum on this curve. If you actually extend this curve, it goes definitely higher than that spot. Okay, and in the same manner, this would be a minimum. Again, a local minimum, because this curve keeps going down. And again, the minimum is a y value. Its location is an x value, and that is a big deal. And it's the distinction between what the minimum or maximum is and where it's located is addressed in the AP exam as well. So please be mindful of that. Now, I need to kind of do a variation on a theme here. Now, that looks kind of like the same curve, kind of. And what I want to focus in on is sometimes what we do is look at a specific interval of a function. Maybe we don't want to look at the entire graph. We're just going to look at a piece of it. Okay. Well, if that's true, okay, so let's say I'm looking at just this blue piece, then this maximum right here is actually now an absolute maximum. Now, it's not an absolute maximum for this entire function, but this is an absolute max on that interval. Okay, so there's a distinction between maximums and minimums on an entire function, on an entire equation, a graph, or just on a part of it. Okay, now related to that then, this would be the absolute minimum in that interval. And notice it's not a spot where it goes down and comes back up. It wasn't that. It was just, that's the lowest y value. Okay, so we're just kind of talking in conceptual terms here. So the lowest y value would be an absolute minimum. Okay, and then going along with that, this point right here would be a local minimum for that interval. Okay, now again, assuming that this is a closed interval, and I filled in those dots at the ends to make sure that that was the case. Okay, all right, so that's just kind of a recap of something we've done before. Okay, now one of the things that I need you to be able to do is read these boxes. So what I'd like you to do right now is just pause. Just pause the screen. Okay, the ticker needs to stop ticking. Read it, and I want you to make sense out of it. Okay, now I'm hoping you actually did that. So now the question is, what did you decide it meant? And, you know, do our conclusions match? Okay. Now this is an if-then statement. This is a theorem. This is like back in geometry. We're not going to do a proof with it or anything, but I need you to understand that there is a condition here that needs to be met for the rest of this to be able to be said. Okay. So it says it's continuous on a closed interval. Okay. Closed interval, whatever that means. Okay. So this is the condition for this to work. Okay, this is a conditional statement. If this is true, if we have a function that is continuous on a closed interval, that means that we're talking about something that starts somewhere and stops somewhere, and the endpoints are included. Okay, so closed interval means the endpoints are included. Okay. If that's true, then it has a maximum value. Remember, the maximum value is a y value. And it has a minimum value, also a y value, somewhere on this interval. So if I was looking at this particular little sketch that I just made, well, this is the lowest spot on that interval. So this is the minimum. Okay, it is an absolute minimum. Okay, and then on the other end, this thing happens to be the maximum. It also happens to be an absolute maximum. Now, it's possible that if you have something like a closed interval, you could have more than one maximum or minimum. Okay, so like this is a local max. This would be an absolute max. And then, same idea, this would be an absolute minimum. And this would be a local minimum. Okay, now one of the things I need you to see here is maximums and minimums can happen at endpoints. And maximums and minimums can happen at these spots where, you know, we get down to a bottom and we turn, and we get to a top and we turn. Okay, so maximum and minimums can happen on either of those. Okay, so let's get back to what this says. The extreme value theorem says if continuous on closed interval, then there is a max and a min. It doesn't say where they are. All it says is, yep, there is one. Okay, so again, extreme value theorem says if it's continuous on a closed interval, then there is a maximum and minimum. It doesn't talk about how to find it, doesn't talk about where it is. Okay, so just a quick little point here. It could be at an endpoint, could be at a spot where it's at a top or a bottom, where it's turning around. Okay, all right. Related to this is the definition of something called a critical point. And this is pretty simple, but all it says is a point on the interior of the domain, so not necessarily on an endpoint. Okay, so if we're talking about on an interval, we're talking about in between the endpoints, not on the endpoints. Okay, and then we're looking for a spot where the derivative is 0 or the derivative does not exist. Now remember that derivatives don't exist at corners, cusps, any place that it goes vertical. Okay, so if the function is if the derivative is undefined, sorry, that's kind of a bad way to say that. Let me back up. Let me get that off the screen if I can. Possibly get that off the screen. Sorry about that. Okay, so if the function goes vertical, or if it's not continuous. Okay, so those are places where the derivative does not exist. Okay, so that's what a critical point is. Okay, again, where the derivative is 0 or the derivative does not exist. Okay. Okay, so that's what a critical point is. Again, it is a point on the interior of the domain of a function, or on the interior of an interval of a function, where the derivative is equal to 0 or the derivative does not exist. Okay, so what we're going to do now is do a little bit of practice here. Now, initially, these graphs come directly from page 194 in our calculus book, and the questions are asking us to identify each x value at which any absolute extreme value occurs. Okay, so we want, sorry, that is funny. That didn't need to happen right then. We need the x values for absolute extreme. Now, just a reminder that the extreme itself, the maximum or minimum itself, is a y value. I just don't know those y values. So all we're trying to do is identify the x values and explain how your answer is consistent with the extreme value theorem. Okay, now first of all, remember that the conditions has to be continuous on a closed interval. Okay, has to be continuous on a closed interval. Okay, so look at number 6. Again, this is taken right out of the calc book. Okay, this point right here is a local minimum. This point right here is an absolute minimum. And this point right here would be an absolute maximum. Okay, so we're going to say absolute max at x equals c, and absolute min at x equals b. Okay. Now, how is it consistent? Now, remember the conditions again are on a closed interval. Well, we're on a closed interval. Okay, we're going from a to b inclusive, and then all it says is there is a maximum and a minimum. That's what the whole extreme value theorem says. Okay, if you're on a closed interval, continuous closed interval, then there is a max and a min. Well, I'm on a continuous closed interval, and look, there's an absolute max and an absolute minimum. Okay. Okay, looking at the next one. Well, the minimum would be here, but it doesn't exist there. Well, it exists, but up here. There could be a maximum here if that was filled in. Well, here's the issue. There actually is no max or min, but I thought that the extreme value theorem said there had to be a max or min. But remember, it's only if it's continuous. Well, this is not continuous. And it's also not a closed interval because it never gets to these points. Right? This goes from A to C, not the same thing as from A to C. Sorry. Okay, so it has to be a closed interval. Now, I'm not saying there can't be a max or a min. I'm just saying there doesn't have to be a max or a min. Okay, so again, the extreme value theorem says if continuous on closed interval, then there's a max and a min. Okay. Well, looking at number 10, this is not continuous on a closed interval. It is a closed interval. It goes from A to B inclusive. It includes a point at A, it's just not continuous. Okay, and now, just for the record, there is an absolute max on this, and it is located at x equals A. That is an absolute max. It is the highest y value on the entire interval. There is an absolute min. But again, as this relates to the extreme value theorem, all we're saying is that there doesn't have to be an absolute max or min if the interval is not continuous or closed or whatever. Okay, so those conditions, if those conditions are met, then there will be. If those conditions aren't met, we don't know. Okay, all right. Okay, so we need to do some more mathy kind of examples. Okay, so this is number 12, again from page 194. Just stealing some of the even problems here. Okay, and what we're again supposed to do here is, now it says use analytic methods. The analytic methods basically mean, oh, that was nice. Analytic methods basically means use derivatives as we can. Okay, now analytic, or they could mean use algebraic methods, not a graphical method. Now we are going to tie this in with you know, how things look as well. Okay, so let's talk process. If we think about the shape of things, okay, and I know I just keep going back to this cubic graph, sorry. Think about the slopes. Where I have a maximum point, the slope is going to be 0. Where I have a minimum point, the slope is going to be 0, assuming that we have a smooth, continuous graph. Okay, in other words, it's differentiable everywhere. Okay, like polynomials are and stuff. Okay, so one of the places where we could have a max or a min is where the slope is 0. One of the places where we have a max or a min is where the slope doesn't exist. And one of the places we could have a max or a min would be at an endpoint, okay, endpoint or the other endpoint. Okay, and again, so like if I just look at this graph from here to here, this would be a max, and this would be a min, if I'm only looking at that interval, okay? All right, so here's what we're going to do. Here's the analytic process for finding maximums or minimums, okay? Analytic process, okay? We need to find the critical points. Remember, the critical points again are where y prime equals 0 or y prime does not exist, okay? And then we also need to look at endpoints, okay? All right, so here we go. We're going to look at the critical points for g prime, or for g of x rather. Critical points again are where the derivative equals 0. So g prime of x, well, the derivative of e to the negative x is e to the negative x times derivative of the inside. Okay, so we want to know where negative e to the negative x is equal to 0. So e to what power, now those negatives don't cancel out, okay? This negative is in an exponent, this negative is like part of the coefficient. You can think of this as -1 times e to the negative x if you prefer. But again, what we're looking for is when will this be equal to 0. Now, just a quick reminder that if x was equal to 0, then negative e to the negative x would actually equal -1, because this thing would be 1 and then you'd make it negative. Okay, so x, that's not it. Okay. Now, you may or may not recall that when you have exponential decay, now okay, I'm going to do a couple little graphs here. If I had just e to the x, that's like 2.718 to the x, would look like this. The negative x in that exponent actually makes it go this way. And then if I go put a negative in front of the whole thing, it flips it up over the x-axis and it actually looks like this. So this is really y equals negative e to the negative x. Well, where's the slope going to equal 0? I mean, the slope gets closer and closer to 0 here, but it never actually gets to. The slope doesn't actually get to 0. In other words, going horizontal, it's not perfect. If I was going to try and solve this, you know, algebraically, e to the negative x equals 0, I'd be looking at log base e of 0 equals negative x. In other words, the natural log of 0 equals negative x. Well, what's the natural log of 0? There's no such value. So there are no critical points for this graph. So if there are no critical points, that's not going to help me. All I can look at then are the endpoints. Okay, so what I'm going to do is I'm going to grab this equation, y equals e to the negative x, and I need to see what's going on at the endpoints. Sorry, I'm just flicking around here. Okay, so y equals e to the negative x, and again, I'm looking between -1 and 1. Okay, so the endpoints for this thing are going to be -1. Now, if I put -1 in here, then I'm going to do e to the negative of, or the opposite of, -1. So e to the 1 is e. The other endpoint would be x value of -1, and then e to the negative of, sorry, I did -1 again. Slow down, Sanford. Put in +1, and I'm going to do e to the negative of that 1. Well, that's 1 over e. Now, just a quick little reminder that e is about 2.71-ish. So this guy right here is 2.71-ish. And this guy over here is like 1 over 2.71. Okay, so the only maximums and minimums on this interval. Okay, now if I go, here's that graph I was not looking at, right, because I'm supposed to do analytic methods. Here's that point, -1. Oh, I graphed the derivative. That's not what I wanted to graph. I'm sorry. I did want to find out where it was equal to 0, and it never did. All right, sorry. So this is that point, negative 1, e, and this would be that point 1 over e. Well, that's the whole graph right there. Okay, so I have a minimum of 1 over e at x equals 1. I have a maximum that's equal to e at x equals negative 1. Okay, so I found minimums and maximums using analytic methods. Okay, now I used a graph to illustrate it, but that's not the method I really used to do the whole problem. Okay. Okay, so this is number 27, again out of your book from page 194. Again, this is the Finney, Demana, Waits, Kennedy calculus book for our AP class. And what, again, we're supposed to find out what the extremes are, any maximums or minimums. This is the last example we're going to do. And I don't want to go much longer than this, but I want to do one example, start to finish, without crazy interruptions. So here we go. Again, to find extremes, we need to look at critical points. And that's where the derivative is equal to 0 or the derivative does not exist. Okay, so I guess that makes sense that we should probably find the derivative. Now, this is 3 plus 2x minus x squared to the 1/2. So this is going right back to chapter 3. Okay, just so you know, we are not going to ever get rid of this stuff as we are doing calculus this year. Okay, so again, power rule with a function inside it. So we're doing 1/2. We subtracted 1 from the exponent, and then we're going to do derivative of the inside. Derivative of 2x is 2. That's 2x. Okay, I want to know where this whole thing is equal to 0. Okay, now I think that this is going to be easier to work with if we do just a little bit of simplifying. Now, this is really 2 minus 2x over 2 times the square root of, I'm going to go ahead and leave it as a square root, I think. Okay, apparently I'm square root impaired. Okay, and again, I'm trying to make this equal to 0 because that's where critical points are. Now, worth noting that I do have a factor of 2 here that I can divide out. And if I do that, this is now 1 minus x. Sorry. And I want to make that equal to 0. Okay? All right. Now, what's really interesting about this is, remember, to solve a rational equation, you just multiply both sides by whatever the least common denominator is. So what I'm going to do is multiply both sides by that big ugly square root. And the cool thing about it is I just really end up with 1 minus x equals 0, x equals 1. So there's a critical point at 1 something. Critical point at 1. Now, I don't know whether it's a maximum or a minimum, or even if it's either of those. Okay, and then to find the y value, you always go back to y. Okay, so I'm going to take this 1 and put it right there. Okay, so this becomes y equals the square root of 3 plus 2 minus 1. Okay, because I'm just putting in 1, so that's 5 minus 1 is 4. Square root of 4 is 2. So there's a critical point at 1, 2. Okay, that's where the derivative is equal to 0. Now, the other issue is I need to look at endpoints. Now, notice I haven't looked at any graph or anything at this point. All I'm looking at is these values. A maximum or a minimum is going to happen at a critical point or at an endpoint. Okay, so we need to look at the endpoints. Now, one other little issue here is, remember that you can only take the square root of things that are positive. There are no endpoints specifically stated here for this thing, but there are endpoints of this implied by the fact that you're taking a square root. Remember, the domain of a function is really about what x values you're allowed to use, and this thing only has certain x values that are allowed. I can't take the square root of a negative. So whatever I'm taking the square root of has to be greater than, the inside of that has to be greater than or equal to 0. So in other words, 3 plus 2x minus x squared, I really want to know where that's equal to 0. And then the values then those will be boundaries, those will be endpoints. Okay? So I need to solve this. This is going to give me endpoints. Okay, so this is all the pre-calc stuff coming back. This is all Algebra 2 and pre-calc coming back. Okay, so this is really negative x squared plus 2x plus 3 equals 0. I am not a fan of negative leading coefficients, so I'm going to divide or multiply through by a negative, or negative 1 if you prefer. Okay, so this is x squared minus 2x minus 3 equals 0. I think that's something I can factor. So the endpoints of this are 3, negative 1. Okay, so let's look at what we got going here. I have endpoints, and I have critical point. The one critical point I have is at 1, 2. So the question is, what do I have going on here? Well, those endpoints, it'd really be nice if I had some y values for those. Okay, so let's just remind ourselves what the equation was originally. Okay, square root of 3 plus 2x minus x squared. Okay, so what I'm going to do is put in 3. Okay, so y of 3 is 3 plus 2 times 3 minus 3 times 3. So that's 0. So 3, 0 is a point. Okay, and then y of negative 1. Okay, so I'm doing the square root of 3. Now, this is funny. This doesn't even make sense right here, because I already know what this is. I'm sorry. 3 plus 2 times negative 1 is negative 1. I'm sorry, is negative 2. Okay, minus 1 is the square root of 0 equals 0. Okay, so that should have been obvious, because I just solved the inside equaling 0. Duh. All right, that's okay, we tracked it through. All right, so let's just recap what we got going on here. Okay, critical point at 1, 2. I have 2 endpoints. Maximums or minimums happen either at the critical points or at the endpoints. Okay, so the only other thing, there is one other little issue that we need to address, and that is the derivative doesn't exist at any place that the denominator is 0. And those are also critical points. Okay, so if the denominator equals 0, those are critical points also, because the derivative doesn't exist. Now, please note that this whole thing is going to equal 0 at the same place as these points are endpoints for the function itself. Okay, so I'm really curious to look at the graph of this. I know this is really going long, and I'm sorry. All right, so there is an absolute max of 2 at x equals 1. How do I know that? That's the biggest y value. There is an absolute minimum of 0 at x equals 3, and also at x equals negative 1. Okay, I just want to do one thing, and I know you need to be done, and so do I. Okay, I'm going to pop up a little graph of this thing. Okay, this will be quick. All right, so here's a graph. Well, this is on the equation. This is the equation in the calculator. Okay, and then let's just push graph and take a peek at this. Okay, so what we said was there is a minimum, an absolute minimum of 0 at negative 1 and at 3. We said that there is an absolute maximum of 2 at x equals 1, and that all bears out with this. This is actually a circle. I mean, who knew? Well, semicircle. Who knew? That's pretty cool. All right. Sorry it went long. It went crazy long. I didn't intend on it going this long, and I will see you in